Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, R-CADT, presents the conference. Image Processing Using Convolutional Neural Networks. Lecture edited by Jesus Velasquez Bermudez. Convolutional Neural Networks. Convolutional Neural Networks, CNNs or ConvNets, are deep learning models specialized for processing grid-like data, like images, using convolutional layers with learnable filters, kernels, to automatically detect hierarchical patterns, from simple edges to complex objects, making them the standard for computer vision tasks like image recognition and classification, while also applicable to text and audio. They mimic the human visual cortex by processing local receptive fields and reducing parameters through shared weights, allowing them to achieve high accuracy with less preprocessing than traditional methods. Text built by AI Google. How do CNNs work?
Convolutional layers, filters slide over input, e.g., an image, creating scalar products to create feature maps that highlight patterns such as borders, textures, or shapes.
Feature hierarchy, the first layers detect basic features, while the deeper layers combine these to recognize more complex parts, eyes, wheels, and finally whole objects, faces, cars. Grouping layers, reduce the spatial dimensions, size, of feature maps, making the network more efficient and robust against small displacements in the position of objects. Fully connected layers, flatten final feature maps and connect them to traditional neural network layers for final classification or prediction. CNN's process should be interpreted as follows. The complete image is taken, in this case a zebra, which is filtered until a partial profile of the image is obtained, in this case the profile of an animal. It could be a horse, a dog or a zebra. It is assumed that this is the universe of animals to be classified. As the universe of animals grows, the size of CNN will grow. The pooling, or convolution process, ends with a flattening layer. From that moment on, the reconstruction of the image begins. Using a fully connected layer, the original image is selected, which can become a generic zebra or the specific zebra. This process is equivalent to an information integration process. The convolution is performed by functions of the ReLU kernel. The fully connected layer learns a nonlinear function in that space. Adding a fully connected layer is an inexpensive way to learn nonlinear combinations of the features represented by the output of the convolutional layer. The input image is converted into a shape suitable for a multi-level perceptron and can be flattened into a vector column. Flattened output feeds a neural network, and backpropagation is applied to each iteration of the training. The model can distinguish between dominant features and certain low-level features in images and classify them using the softmax classification technique. There are several CNN architectures available that have been key to building algorithms that drive and will drive AI for the foreseeable future. Integration is performed by the functions of the softmax kernel. The image shows the sequential connection of the two types of layers. Pooling layer and fully connected layer. This video demonstrates the pattern recognition capabilities of CNNs. High associates image processing with mental intelligence and pattern recognition. Mental model is oriented to identify patterns, its foundations are not mathematical, and respond to data processing and evaluation of eventual and systematic experiences. It is based on good practices. Pattern recognition is a data analysis method that uses machine artificial intelligence algorithms to automatically recognize patterns and regularities in data. This data can be anything from text and images to sounds, or other definable qualities. Pattern recognition systems can recognize familiar patterns quickly and accurately. Pattern recognition is the activity that most performs the human being, for example identifies images of people, foods, hydroclimatic conditions, traffic conditions, texts, sounds, and etc. All this with the aim of establishing the conditions of the environment, in the past, the present, and the future, and based on this knowledge make decisions. How the brain identifies patterns is not properly known, but it is mimicked by traditional artificial intelligence. Deep neural networks, DNNs, are based on neural networks composed of neurons with some activation and parameters that transform input data, such as UAV remote sensing images, into outputs, such as land use and land cover maps, while progressively learning higher-level features. This progressive learning occurs in layers between input and output, which are known as hidden layers. A DNN architecture can be built from an initial layer, X input, composed of the collected data samples. Subsequently, this data information can be extracted through hidden layers in a backpropagation form that is used by the subsequent hidden layers to know the characteristics of these entities. At the end, another layer is used with a trigger function related to the given problem, returning a prediction result, Y-label. A DNN can be made up of different architectures, and the complexity of the model is related to how each layer is implemented. Different architectures are regularly proposed. Convolutional neural networks, CNNs, recurrent neural networks, RNNs. Deep belief networks, DBNs, Ball et al., and more recently R, and generative adversarial networks, GAN, Goodfellow et al. For image processing and pattern recognition, most of the current research focuses on CNNs. Since 2012, Krzyzewski demonstrated a method that won an image classification contest by a wide margin in his favor. The network, which came to be known as AlexNet, was built with 8 layers, in which the initial 5 layers were all convolutional, some followed by layers of maximum grouping, and finished with 3 fully connected layers, all use the ReLU activation function. The success of this method was associated with its depth. Neural networks have evolved to allow machines to recognize patterns, so that they appear to see the world as humans do, perceive it similarly, and use knowledge for a multitude of tasks such as image and video recognition, the analysis and classification of images, the recreation of media, recommendation systems, natural language processing, etc. Over time, advances in computer vision with deep learning have been built and refined, mainly on top of one algorithm in particular, the convolutional neural network. The architecture of a CNN is analogous to that of the connectivity pattern of neurons in the human brain and was inspired by the organization of the visual cortex. Individual neurons respond to stimuli only in a restricted region of the visual field known as the receptive field. A set of these fields overlap to cover the entire visual area. An image is an array of pixels in 2 dimensions, which can be flattened by a vector. A 3-to-3 matrix can be converted into a 9-to-1 vector, which feeds a multi-level perceptron for classification purposes. In cases of extremely basic binary images, the method could make predictions but would have little or no accuracy when dealing with complex images with pixel dependencies throughout the image. A CNN can successfully capture the spatial and temporal dependencies of an image by applying relevant filters. The architecture is better suited to the image dataset due to the reduction in the number of parameters involved and the reuse of weights. In other words, the network can be trained to improve the image. In the figure, we have an RGB, red, green, blue, image that has been separated by its 3 color planes, red, green, and blue. There are several color spaces in which images exist: grayscale, RGB, HASV, CMYK, etc. You can imagine how computationally intensive things would become once the images reach dimensions, say 8K, 7680 x 4320. CNN's role is to reduce images to a form that is easier to process, without losing features that are critical to getting a good prediction. This is important when we're going to design an architecture that's not only good for learning features but is also scalable to massive data sets. Convoluting a 551 image with a 331 kernel to obtain a 331 convoluted function. The image dimensions are equal to 5, height, per 5, width, per 1, number of channels. RGB A331 matrix is selected, the green section resembles the 551 input image. The element involved in the convolution operation in the first part of a convolutional layer is called the kernel or filter, represented in yellow. In the lower right corner, in red, the K-core is shown. The convolution operation consists of multiplying the floating part, numbers of the floating array in yellow, by the nucleus K in red, and adding the results. The nucleus is shifted 9 times due to stride length is equal 1, non-striated, each time a matrix multiplication operation is performed between K and the floating portion P of the image on which the nucleus is floating. The filter moves to the right with a certain stride value until it analyzes the full width. As you continue, jump to the beginning, left, of the image with the same step value and repeat the process until the entire image is covered. Convolution operation on an N3 image array with a 333 core. The filter moves to the right with a certain step size until it analyzes the entire width, at which point it jumps to the beginning, to the left, of the image with the same step and repeats the process until it goes through the entire image. For images with multiple channels, such as RGB, the core has the same depth as the input image. The multiplication of matrices is performed among all the pixels, and the results are summed with bias to obtain a convoluted output of a flattened channel of depth equal to 1. Convolution operation with stride length equal to. The goal of the convolution operation is to extract the high-level features, such as edges, from the input image. ConvNets don't need to be limited to a single convolutional layer. Conventionally, the first CNN is responsible for capturing the low-level features like borders, color, gradient orientation, etc. With added layers, the architecture also incorporates high-level features, providing us with a network that has a healthy understanding of the images in the dataset, like how we would. There are 2 types of outcomes for the operation, one in which the convoluted feature is reduced in dimensionality relative to the input, and another in which the dimensionality increases or stays the same. This is done by applying the valid padding in the case of the former, or the same padding in the case of the latter. Case: Cole blend optimization using convolutional neural networks. A reported reference is presented in the article. A surrogate-assisted intelligent adaptive generation framework for cost-effective Cole blending in thermal units. This paper proposes an adaptive method of condition classification, based on GPT-type artificial intelligence, generator pre-trained transformer, which determines the probability distributions of the output, the Cole mixing, and completes the interval division based on previous operational data. In Chinese thermal power generation companies, the cost of purchasing fuel accounts for more than 2/3 of the total. In addition, the mixing of coal in thermal power plants has a major impact on damage to the plant's auxiliary equipment, as well as on soot and sulfur dioxide emissions. Therefore, the optimization of the fuel mix is of great importance to reduce production costs, in addition to contributing to energy conservation and emission reduction and promoting the sustainable development of the national economy. Optimization is critical to increasing operational efficiency and reducing emissions from the company's boilers. A mathematical model has been implemented that considers the price, caloric value, ash content, volatile matter content, moisture content and sulfur content of coal.
La metodología se utilizó en la central térmica operada por Babcock & Wilcox Beijing Company Ltd, BAN-W. Se presenta el caso de una unidad de generación a carbón de 350 MW, realizado durante las importantes fluctuaciones del precio del carbón causadas por las condiciones internacionales en 2021 a 2022. El rendimiento de esta unidad se vio notablemente afectado, con un marcado aumento en los costos de generación.
The methodology was used at the thermal power plant operated by Babcock & Wilcox Beijing Company Limited, BAN-W. The paper presents the case of a 350 MW coal-fired generation unit, built during significant coal price fluctuations caused by international conditions in 2021 to 2022, and the performance of this unit was markedly affected, with a notable increase in generation costs. The image presents the diagram of the thermal power plant in Shaara, Georgia. Coal blending, CBS, strategies have a considerable influence on coal generation. Among them, the cost of coal is determined directly by CBS and typically accounts for more than 70% of the total operating cost, making it a central concern in cost management. Other costs related to CBS are ancillary costs, which are significantly affected by coal quality indicators, such as sulfur and ash content in blended coal. The image shows the flow of information during the process of mixing coal and electricity generation, which as a byproduct produces polluting emissions. To address these problems, the authors propose a methodological framework for generating cost-effective CBS, blends. The framework includes a unit recognition of output conditions, UOCR, module, which enables adaptive classification of output conditions based on historical operational datasets, performing intelligent condition recognition with imitator and pre-trained image classification models, like GPT, using combination strategies and unit parameters as inputs. The generation of profitable strategies, CESG, module uses a surrogate model to assess the economic viability of strategies in terms of environmental and carbon costs, among other factors. The UOCR is also used as another surrogate model to validate the viability of the strategy. Profitable strategies are generated using a population-based meta-heuristic algorithm. In the case study, the UOCR achieved an average training accuracy of 96.64%, and the cost-effective strategies generated reduced costs by an average of 3.37%, compared to the strategies currently implemented. Hy prefers to combine the GPT methodology with a model based on mathematical programming. The generation of profitable strategies, CESG, module uses a surrogate model to assess the economic viability of strategies in terms of environmental and carbon costs, among other factors. The UOCR is also used as another surrogate model to validate the viability of the strategy. Profitable strategies are generated using a population-based meta-heuristic algorithm. In the case study, the UOCR achieved an average training accuracy of 96.64%, and the cost-effective strategies generated reduced costs by an average of 3.37%, compared to the strategies currently implemented. Hy prefers to combine the GPT methodology with a model based on mathematical programming. Imitator is a novel convolutional neural network that transforms CBS and other inputs into dimensions compatible with carbon features into image classification models, allowing pre-trained models to perform recognition of output conditions, carbon mixing, and resulting features. The imitator assimilates an input or output matrix to an image. This is true when you consider that images on a computer are stored in arrays of pixels. For imitator, the charcoal's matrix of characteristics is equivalent to an image. The input matrix is unit parameters resulting from several steps performed by CBS. The design of imitator is based on a combination of attention mechanisms and transposed convolution matrices that are used for feature extraction and input transformation. The result matches the common input dimensions required by pre-trained image classification models. The imitator assimilates an input or output matrix to an image. This is true when you consider that images on a computer are stored in arrays of pixels. A CNN applies a set of convolutional filters to the input images. Each filter activates different characteristics of the images, allowing for fast and effective training. Instead of images, we can have input and output matrices, from past coal mixing experiences, that relate the input parameters to the mixing done. The design of imitator is based on a combination of attention mechanisms and convolution matrices that are used for feature extraction and input transformation. The result matches the common input dimensions required by pre-trained image classification models. The table shows the description of the data for the input parameters in the dataset. Classifying the unit output condition involves dividing the power of the generation plant into different ranges according to magnitude, while categorizing the CBS and plant parameters. In this case, the operating range of the plant has been divided into 6 conditions, starting at 180 megawatts, and for each of them an independent model is calibrated. The graph shows the fit in the training and verification phases. The figure shows the comparison between the original empirical classification of gray and the adaptive classification, in multiple colors associated with the ranges. The actual dataset production was concentrated between 180.0 and 307.1 megawatts. In the theoretical set, the range extends to the capacity of the plant, which according to the adaptive classification is not achievable. This failure in the estimation will bring undesirable consequences by establishing agreements on a theoretical capacity, which the coal mixture does not allow in practice. The adaptive method significantly improves the granularity of conditions, allowing for a higher level of refinement in CBS. The figure shows the profitability of AI-generated CBS and strategy based on a mental model, backed by intuition and experience. The results for the 6 operating ranges of the plant are presented, in terms of total cost, cost of coal and other costs. The table shows the comparison between the CBS generated by artificial intelligence, and the original strategy generated by a human. For the 6 conditions of the total coal flow, the proportion of carbon A is presented, and that of B, the proportion of carbon B with respect to that of carbon C. Data on the total cost, cost of coal, and other costs are presented. In general, CES can produce differentiated and cost-effective CBS adapted to various conditions. These strategies meet the practical production constraints in terms of production conditions and coal quality, significantly reducing total costs compared to the original strategy, and demonstrate great robustness and applicability. Bandwidth strategy to define an intelligent, adaptable and cost-effective CBS, assisted by artificial substitutes, generates a methodological framework that reduces reliance on human expertise in decision-making and significantly improves the economic efficiency of coal blending strategies. The CESG is designed with a surrogate-assisted model to comprehensively assess the cost-effectiveness of the strategy and impose constraints on the generated production conditions and coal quality requirements based on the UOKR, producing cost-effective CBS using population-based meta-heuristic algorithms that, on average, reduce total costs by 3.37% and the cost of coal by 3.62%. Under some production conditions, the cost reduction reached total cost 8.7%, and the cost of coal 6.3%.
Like Herbert Simon, Hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.